Okay, welcome everyone to the session 7 of this year's Data Academy. My name is Yumi Choi. I'm a member of Community Science team, and this session is going to talk about deep coadds and the object table. All right. So this year's Data Academy is again focused on beginner level use of the RSP and the DP1 data products. And there are 12 sessions in total. Each of them are repeated in morning and evening for a global audience. And we have drop-in Q&A sessions today, one right after the morning session and the other one right after the evening session. So if you have any questions, please come to the drop-in Q&A sessions. And the last two sessions this year, um, session 11 and 12, will talk about the upcoming DP2 and prom products. So all the informations about this year's academy and including the slides and the recordings for each session will be available in the website. Okay, before we talk about the deep coadds and the object table, I will go through a few reminders. The first one is the community forum. So community forum is the place to go if you have any problems with using the RSP or using the Rubin data products. So in the forum, there is a support category. This is the place you make a new post about your problems or questions. So when you make a new post, please provide the descriptive titles and some details about your problems. Maybe you can copy and paste your error messages and also provide us some context so we can understand your problems better and even reproduce the problems and try to provide the solutions to your problems or questions. So CST members are regularly monitor the support category, but also the other Rubin steps or even like experienced community users can provide solution to your questions. And all the documentations about the DP1 can be found at dp1.lsst.io, including all the tutorials cover today's session as well as entire Data Academy. And the DP1 overview paper has been recently published, so you can cite the DP1 paper properly. And the documentations also have the relevant DOIs to use. So please cite the DP1 and the DP1 data products properly if you use them in your work. And in the Rubin Observatory official website, under the For Scientists section, there are a lot of informations you could find, from the announcement and news and events about the observatory, but also all the tutorials and documentations and the resources you could use for many other cases. Okay, so this is the agenda for this section. First, we go over the data processing, basics about the data processing for images and the catalog and the object table and the data products, deep coad images and the object table. And then we're gonna do some live demos, both for the portal aspect and the notebook aspect. Okay, so first key concepts. So the DP1 provides the sky map, which is an all sky tessellation grid that are subdivided into tract and patches. So sky map used for DP1 has about like 19 K tracts. It's covering roughly 2.8 square degrees, and each tract is further divided into 10 by 10 equal-sized patches. And each patch is covering about the 1 ccd size in the sky. So you can think of there is a sky map, and then it's divided into tracks, and then each tracks are further divided into patches. And the LSST specific terminology here is the object versus the source. So source, like source table, we mean the detections in a single processed visit image. So the source are the measurements made on the visit image, while the objects uh, means that the detections made in the deep coed images. So we have like source table reporting the measurements made in the individual visit images, and the object tables uh, uh, may have the measurements in the deep coed images. All right, so data processing. So the Simone telescope take a bunch of images at the same positions of the sky, and we need to combine all those individual visit images into one decoed to get deeper depth, right? And we call those to make those deep coads, we first select what kind of visit image to take as an input. So we're not taking all the visit images, but just the process and calibrate the visit images with PSF full width full width half maximum less than 1.7 arc second. So we're pre-select only the visit images taken in a reasonable conditions. And then we identify all the pixels with the transient features and artifacts, things like satellite trails and cosmic rays. And those pixels are excluded from co-edition. And then once we have the inputs are ready, then because all these inputs were taken with a different position angle and slightly different pointing centers. So we need to align and warp all the input images onto a common pixel grid. So we did that, and then stack all the images weighted by the inverse variance. And um, while individual calibrated visit images were already background subtracted, maybe there is some residual background in the deep coed. So after register all the images on a common combine all the images, we do measure a constant background residual and subtract it from the deep coed. So in this image combination processing, the end product is the deep coed images. So each covering a single patch of the sky, and the units are in nanojansky. All right. So the object detection and the measurements. So now we have deep coed images in all 6 filters, right? And from each deep coed, we detect a footprint, something looks like this, with the signal to noise ratio greater than 5. So this is a single footprint with a multiple peaks, but some of the footprint might have an isolated peak, just single peak. So it depends. So once we define a footprint with a signal to noise greater than 5, then the footprint are deblended into multiple peaks. We call it child peaks using this scarlet light. And then in each deep coed, after deblending, we make a flux measurements and the shape and size measurements and all kinds of measurements at the locations, at the fixed location across all filters. Um, and so because we we make a measurements for a footprint with detection ratio greater than 5, if that uh, and then we deep blend the footprint into multiple picks. So the first measurements of individual picks could have signal to noise ratio less than 5. Um, and this process, the end product of this process is the object table, which only has the unique object. It doesn't, it already removed all the duplicates. If the same source was detected in multiple band, and we just cross match and then just assign one coordinates for that source, so there's no duplicates. And also the track and patches are overlapping a little bit at the edge, and then we remove the duplicates in those overlapping area too. So the way to access to the deep coad image is to use Butler or simple image access SIA service and the tab service. So there are multiple ways to access to the deep coad images. I think this is covered in the previous sessions. And in the DP1, there are 2,644 deep coed images. And each deep coed has like 2D arrays of pixel data. And we have three planes. First one is the image plane. In other words, science plane, or and the variance plane, which is for the uncertainty and the flux and the units of the square nanojansky. And we also have mask plane. This is the integer bit mask. Um, so it has all sorts of different types of mask, and different types of mask has a different bit. And so the values of this mask plane represent a unique combination of the masked types. So we'll get to a little more detail in seconds. And the deep-coded image also has the metadata, which include like list of input visit image. So what kind of input images were used to generate this deep code? That information is available, and also the PSF information is available, and the photometric calibration information is available, and the WCS information is also available. All right. And the object table, the way to access to object table is either via tab service or the Butler. But for the table, using the tab service is a recommended way. But for the object table, um, it has about like 1,300 columns. So it has a lot of columns. So you need to specify which columns you wanna use for your science. So we'll get to that, how to figure that out in a second. And the key columns, which are maybe the most popular columns we all are interested in, are the unique identifier, the object ID. So this is the object table doesn't have any duplication. So it's all unique sources detected in the object, in the deep coed images of any filter. So it has the coordinations and the flux measurements in nanojansky. The flux measurements were made in various types like PSF flux, seam-outer flux, Sarsic flux, and the Cron flux and aperture flux at various radius. And also the magnitude. It's in an AB Mac system, but in the table, only the PSF flux and the CMODA flux are pre-converted to the magnitude, but you can convert the other fluxes to magnitude in various way. And we also, the table also has the Milky Way foreground dust raining values from the Schlegel map, the recalibrated ones. We also have the HSM shape parameters. So you can measure like shear or the PSF size using this kind of measurements. And plus, there's variety of flags that are associated with all kinds of measurements and also about the mask. All right. And now let's move on to the live demo. We will start with the portal aspect, but maybe I'll pause here and see if there is any question. Okay, if not, let's go to the maybe you can just copy this ADQL query first, which is to retrieve one of the coad image and display it near the ECDF as field. So I already logged into the RSP. If you want to follow along, please go to data.lsst.cloud and select the portal aspect. And here we are going to retrieve the image, right? So click the image tab, and then we just paste the copied ADQL query here to query the deep coed image near the center of the ECDF as fields, and we can click the search. Okay, so this one returned six images in total, one for each filter, right? So we have 6 filters, and maybe in the active chart you can click the details tab, and it has the column names and then the values. So it's the tables for basically the first law in this table in the below. And this deep coed image is the first one highlighted here. But if you click the multi-grid icon, then it displays all 6 images at the same time. And then you can see this the arrows. So as I mentioned, the first image plane is the science image, and then the second one, whoops, second one here is the mask, and then the third one in the variance. So you can, go back and forth between these science, variance, and mask images. And you can do a lot of things in this portal aspect using the toolbox, maybe adding the arrows for the north and east, and then you can manipulate this plots by using these tools and change the colors. But then at the end, you can oh, not this one. Oh, and then you can align all the images by WCS and targets and things like that. So you can play this with a lot to explore the images. Okay, and then the next thing we are gonna try in the portal aspect, now retrieve the object catalog around the ECDFS field again. So edit click the Edit ADQL and just paste the ADQL statement we copied. And this one actually overplots all the objects, all the sources measured in the object table in the deep coad in this field. So it's highlighted. Maybe you can zoom in a little bit to look at how it worked. All right, so you can see the faint, little faint dots here and there, and then all the measurements were reported in those pics. All right. So now we're gonna look at the notebook aspect. So I'm gonna open another tab and select the notebook aspects. Maybe I click this because my computer is heating up. Just reopen everything so we can start from scratch. So first notebook we're going to look at is 202 deep coads. So we go to the tutorial tabs under DP1, 200 level 202 series, and deep coads. Overwrite. Okay. So yeah, the deep coed is the combination of multiple, processed visit images, and deep coeds are accessible with multiple ways, but here we're not gonna show, the various ways of access to the data, but just grab um, deep coed using the butler. And what this cell just did is that uh, we set the default display as a Firefly. So this cell triggered the Firefly viewer tab is activated the windows. And then if you want to look at this Firefly viewers side by side where with your notebooks, you can just drag the tab and then move into the right windows, right parts of the window. All right, so we're ready to display access and display. So first, maybe we can just look at what kind of data set types for the deep coed. So deep coed data set type it's the name, and this is the dimension, the band information, and which sky map we are looking at, and then tracked and patch information, because the deep coed is created per patch. And then exposure F data, which has all the 2D image planes as well as the metadata associated that image data. So yeah, we just extract the dimensions of the deep coed image, and let's query one deep coed images using Butler. So we're searching deep coed images near the center of the ECDFS field, and the Butler found two deep coed images, which means that the deep coeds are slightly overlapping to each other. So this coordinate we set the center of the ECDF fields fall into that overlapping area. So we just will grab the first image here, and then let's display the deep coed in the Firefly. All right, so this is the deep coed image we just grabbed. And And the rest of this section shows a bunch of different ways to retrieve the Bitcoin image. So I'm not gonna go through this, but then and we can do this pixel data image display. Oh, yeah, okay. Now we set the mask transparency to 0, which means it's no transparency for mask plane. So it displays all the mask plane on top of the deep coed image. And if you set it to 100, um, make it the mask plane completely transparent, then it only shows the science, the image plane. Okay. So I said DeepCoed has the exposure F data, and that also includes 2D arrays of image plane and mask plane and variance plane. So now we access to those 2D arrays of each image and then display the image plane in the frame 2. It looks about the same, right? Um, And the let's display the variance plane and also the mask plane. All right. So what we just did is the get mask or get variance or get image, and then just convert it to the astropy, the 2D array, and then display it in different frames. So that's what we did. And then the mask plane looks a little different before when we have a mask transparency equal to 0, which was like all greens then red, right? So to make the the figures the same as we looked in the first frame, we can also just set the transparency to 0. And if you're interested in like detected mask plane only, detected mask, then you can set all the other mask flags to 100% transparency. So it's not displaying, but only set the detected mask flag to 0. So you can see which pixels are detected pixels in this deep coed. All right, so metadata and attributes. So this deep coed has a lot of informations associated with it, right? So it's basically like headers in the standard fits image formats. So we first get the deep coed dot, get metadata, and then we can display what kind of metadata is there, like this, right? So, uh, what is the data set type and what is the band and what is the patch information, tracked information, and sky map information, and what is the units of this image and things like that. And then we can convert that, getting the dictionaries of that metadata and to searchable. Um, and the informations, like as I mentioned earlier, this deep coed also has like PSF information and WCS information. So we now get those informations. Um, so the info is stored, and we figure out what kind of input individual visit images were used to create the deep coed. So there are 236 individual visit images were used to create this deep coed, and how many CCDs were used in this deep coed. processing is like 726, right? And WCS information, we get WCS. And once we get the WCS, we can convert the sky coordinates to the pixels in the decoed and vice versa. So this is just showing how to do it. Um, Once you have some sort of coordinates, then you can convert it to the pixel. And if you have a pixel position, then you can convert it to the coordinates in degrees. And also, you can figure out what is the bounding box of this particular deep coed image. So there is a get bounding box, BB box method. Um, and then you can from that you can figure out what is the corner of the bounding box and calculate the area of the bounding box and things like that, and figure out if your coordinates are inside the bounding box or not, is another usage of this uh, bounding box information. And finally, we look at the PSF informations. So PSF is spatially varying. So if you want to figure out the PSF at the location of your target of interest, then you provide the coordinate information of that location and compute the PSF at the location. And now it shows the PSF at the location inside this deep coed in frame 5. And then you can also calculate the PSF shape and the size. So for example, this PSF has size of like about 5 pixels. All right, so now we have look at the deep coed near the center of the ECVFS field, and we want to look at what kind of sources were detected and reported in the object table in the same area, right? So we are going to access to the object table for the for this deep coed image location. So we're providing tracked and patch information, and then query the object table using Butler based on those tracked and patch information, and then retrieve object in those areas, sky area. And there are about 11,000 objects in this deep coed region. And now we display this deep coed image again, and then overplot all the object in this deep coed. So maybe I can switch to a single frame and then zoom in a little bit. So this is deep coed, and then you can see all the measurements made in this deep coed and then recorded in the object table. Right. Any questions before moving into the next tutorial? If not, the next one we're going to look at is the object table. Okay, you can move here, right? Okay. All right, so I think we already go over how the object table was created. It's all the section in the deep coed and each filter from the footprint with the signal to noise ratio greater than 5. And there is no duplication. And we instantiate the tab service and the Butler service. And first, although we already kind of look at how many columns are existing in the object table in different way, but we can also figure out that using the tab schema. So the tab schema, that columns return all the column information in a dp1.object table. So we did that, and maybe I can close this a little bit. And so, yeah, it returned 1296 columns with column names and data type and the column description and unit. So you can figure out the column names and the description um, uh, using that to figure out which columns you want to use for your science. Okay, so yeah, we already talked about key columns and geometry, right? The fluxes, and maybe I can talk about a little bit about the flags. Um, So pixel flags means that is related with the mask. So what kind of mask flag was set for that object is in here. So if you want to know if the object is affected by cosmic ray or saturation, you can look at the corresponding pixel flag for that. And also, all sorts of measurements have the measurement flags. So if the measurements were flagged for any reasons, the flag is set. So you want to also check that flag. And the deep blending flag is to indicate whether that specific object was deblended from a parent object, which I showed a single footprint has a multiple peaks, right? So in that case, it was deblended from the parent's object, but the object catalog only reports those deblended child peaks in the table. It doesn't have the it doesn't have the measurement information about the parent object, but there is a parent object ID in the table. And there is also deep blendness flag exist, showing how much flux is affected by neighboring. So it's not actually flag, but there is also deep blendedness flag exist, set to either 1 or 0. But there is a blendedness columns which are showing how much flux is affected by neighboring neighbors. Okay, so yeah, this we already saw that there is tables with the column names and column descriptions and units. So we don't need to do this. And section 3 basically is covered by a portal aspect, how we retrieve the object table with the tab service using the ADQL statement, and also how to access to the table with the butler was shown in the deep coed notebook. So I'm going to skip this section 3 completely and move on to the last one. Any questions? If not, let's look at the last one, which is the survey property map. Okay, so survey property maps literally uh, you know, just the maps that describes the survey property, mean property. So they are pre-calculated, pre-constructed maps describing the average, the survey property. So if you have, it's worth checking if the survey properties you're looking for is already exist. So for example, this is the list of the available survey property maps. So for example, deep coed exposure time consolidated map sum, which shows this is the map showing the total exposure time accumulated per sky position. So that kind of that kind of like average um, or consolidated map property maps exist. So you can look at the list and figure out the properties you want to figure out is already created as a map. Um, so in this notebook, we're gonna explore. We're gonna see how we access to those sky the surveyed property maps and use them. So first, let's list all the available maps. So there are like 14 maps in total you could use. Um, and then maybe we can look at the data set types using one of the maps as an example. So it has like band and sky map dimension, and the data is stored as a hill sparse map. Okay. And then the band and sky map are the required dimension for this data set type. And then let's retrieve one of the map as an example. So uh, maybe we're interested in looking at, so we created, so DP1 provides a deep coed, and what are the depths of those maps, right? Or we care about the depths of the deep coads. So we are going to grab the PSF 5 sigma magnitude limit consolidated map to look at that. So first, we need to manipulate the retrieved map. So, for example, we get the map values at the position of interest. So, let's use the central position of the ECDFS field and get the map values. So, at the center of the field, the 5 sigma PSF magnitude in R band, I think we said R band is 27th magnitude. And then we can retrieve the map values at multiple places at once. But if you provide a coordinates that are not available for DP1, it returns a sentinel value, which is very large negative values. All right, so how to construct the map for the entire field. So let's say um, we are interested in the ECDF fields. We want to figure out all the PSF magnitude limits across the field. And then to do that, we first figure out the X and Y coordinates for the entire field to cover the R and that grid for the field. So we constructed 2D like position grid first, and then replace the sentinel values, the big large negative values, pixel values with nan, so we can do statistics without any problems, or visualize the map with any problems. So this is the PSF magnitude limit. In other words, like the 5 sigma depth of the ECDFS field deep coed. So it's mostly like 27th magnitude. All right. And because time, I'm going to skip this section 4.1, which shows how to change the scale and colors of the map. In section 4.2 as well. In this section 5, we are going to plot the deep coed image along with this survey property maps, so we can put them in side by side and look at them at the same time. So we first retrieve the deep coed image and then get the WCS information and also the bounding box information. And then we are going to get the survey maps around that area. And these are all getting the values at the location of the field we're interested in. So this is the plot now. So the top left shows the deep coed science image plane, and then this one um, shows the PSF magnitude limits in R band, and PSF size map, and then sky background map. So this is the mean sky background in the steep coed area. Okay, so I think this is all I want to show in this session. And I'm happy to take any questions. No question?
I don't see any in the chat.
Yep. Okay, maybe I can stop recording.